Okay, we should start it. Yeah, we should
Okay.
start it.
All right, so thank you everyone for coming. We have our very own Alice Harpole to talk to us about some of the exciting work she's been doing with us. Alice has been with us for 1.5 years now. Before joining our group, she was at the University of Southampton, where she worked in the maths, plural, group. Which is basically where the relativity was in Southampton. Before that, she was at Cambridge. And Alice is an expert on all sorts of hydro and GR and fun stuff, and she's helping us blow up stars with all that.
Thank you. So I'm going to talk today about the work that I've been doing modeling low Mach number astrophysical flows. So I'm going to start off by talking about what exactly that is, and then talk about some astrophysical applications and a bit more about the code that we use to model them. Okay, so first, what is low Mach? So lots of flows in astrophysics are what we call low Mach number. So essentially that means that the speed of propagation of a flow is a lot less than the speed of sound. So if you take the ratio of the velocity of the fluid and the sound speed, it gives you the Mach number, and that's a lot less than 1. So examples of this are convection in white dwarfs for type 1a supernovae. So we haven't got a photo of that, but there's a nice image of a type 1a supernova remnant. There's type 1 X-ray bursts. So I'll talk a bit more about these later. These are essentially explosions of neutron stars. Classical novae. So again, we've got the central picture here. Is a nice. Oh, thank you. I never know how to use these things.
I couldn't figure it out either.
Okay, the central one here. This is a nice classical nova, and stellar convection. So kind of nice convective motions in the interiors of stars, as you can see from this artist's impression here. And I'll talk a little more about both type 1 X reverse and stellar convection later. So why do we care about this? So when it comes to modeling these systems, if we use standard compressible codes, then it turns out we need really very many small time steps to capture the very fast-moving sound waves. So this is annoying if you're trying to model a very slow-moving flow, because you're having to use these really small time steps to capture the sound waves, and you don't really care about them. So this becomes very computationally expensive. So it means if you want to do a simulation that's both high resolution and goes over a long time scale, then this can just become far too computationally expensive for us to model. So the good news is we have something called low Mach number methods. So these are essentially an array of lots of different methods that allow us to use much larger time steps. So this means we can then do our high resolution, long time scale simulations. And there's a number of ways that we can achieve this. So the way that I'm going to talk about, what we do in our codes, is we modify the hydrodynamics equations to essentially filter out these sound waves. So that means we can kind of ignore them. We're no longer constrained by these fast-moving sound waves, and we can use much longer time steps. Now there are other methods to do this, which can include implicit methods, preconditioning methods, and artificially boosting certain physical quantities, but I'm not going to talk about these anymore. But there are other ways to do it.
A quick question
Yeah.
from a non-expert. What's the connection between a low Mach number method and the incompressible approximation?
That's my next slide.
Right.
Okay, so now I'm going to take you on a kind of a history lesson of the development of low Mach number methods. So excellent question. So kind of the first one of these low Mach number methods that really came about was the incompressible approximation. Looking at my beautiful image here, so the incompressible approximation essentially means that we assume that we have a constant background density in our fluid. As a result, this means divergence of your velocity of your fluid goes to 0, and all of your sound waves are essentially at infinite speed. So this is filtering out all the sound waves by making them infinite, but it means you can then use much larger time steps. So this is great, but if you are trying to model an atmosphere, then you might have a gradient in your background. So this isn't a very good approximation if you've got something where the background density changes significantly. So the way we can get around that is something called the inelastic approximation. So here my background density can now have a gradient in it. So it's allowed to vary in space significantly. So instead of having our divergence of our velocity going to 0, now the divergence of our momentum is now going to 0 instead. So here we have incompressible, constant everywhere. Inelastic allows this gradient in our background. Now what if we want to have reactions in our fluid? So if we want to have reactions, we want burning, heating, this is going to cause maybe large-scale changes in the density and the pressure. So the inelastic approximation is no longer going to be very good. So we can, the first people to kind of take this into account were these guys. So they used what they called the low-Mach number approximation. So here, if we look at incompressible, this sets the divergence of our velocity to 0. But instead what they did is they set it equal to some source term. So this source term allows these large-scale perturbations in our pressure and density. However, it's at the expense of the constant background. So, so this here assumes that we have a constant background density, but we are allowed large-scale perturbations. So the next thing to come along is pseudo-incompressible, and this basically combines these two approaches. So we are allowed a gradient in our background pressure and density, but we're also allowed large-scale perturbations from our heating. So if you kind of look at this expression that I got here, it's basically a combination of these two. Yeah.
So could you go back just one image? Right?
Yeah.
Okay, that's just what I wanted to see.
Yeah, so pseudo-incompressible, so we have a gradient in our background, pressure and density, but we also have large-scale perturbations from reactions, from heating due to reactions, for example. And then the thing that we use in our code is what is being given various names, but the name that I'm going to use on this slide is the generalized pseudo-incompressible approximation. So this basically takes the original pseudo-incompressible, which was developed for an ideal gas, and extends it to allow a general equation of state. So for our low-Mach number approximation, we can have background stratification, large-scale compressibility due to reactions, heating, stuff like that, and we can have a general equation of state. So, how do we do that? So let's look a bit more at the equations. So we do that by decomposing our pressure into a base state, which we define to be in hydrostatic equilibrium, and we have some perturbation here, this pi term, which is an unfortunate symbol, but one that we're kind of stuck with now. So the ratio of those, the ratio of our perturbation to our background pressure is order Mach number squared. So this is the assumption that we are making for this approximation. If this doesn't hold, then this means our approximation is no longer valid. So we have our pressure, and it's the sum of this background, which depends only on the vertical direction and time, and we have our perturbation, which depends on all spatial coordinates and time. So because we've defined our base state to be in hydrostatic equilibrium, this allows us to define a base state density, like so. Now, in order to be able to capture this background stratification, we also introduce this beta variable here. So this is kind of like a buoyancy term. And using this expression, it basically captures this background stratification. And then all of our local compressibility from reactions and heating and so on, they come in from this source term here. So here we've got these terms here, we've got these burning and heating rates here. Okay, and then we stick them into our equations. So these are the equations that we're going to be solving when we do use this Mach number approximation. So the important terms I've highlighted in red here. But at the top, we've essentially got the momentum. We've got the continuity equation with these mass fractions of species here the x's, because we are going to be looking at burnings, we want to include some species in there. We've got our momentum equation here, our energy equation, and then at the bottom we've got a divergence constraint. So the important red terms here, so if we look at the momentum equation, normally this would just be the gradient of the full pressure, but here we've just got the gradient of our perturbation. And that's because we've used the definition of our base state being in hydrostatic equilibrium. Our base state pressure is actually hiding here. So if we look back at the hydrostatic equilibrium equation, this means we kind of replace this by this, and that term goes over here. Then if we look at our energy equation, normally in the full compressible equations, we'd be using the full pressure here, but instead we're using, because we're throwing away higher order terms, because we've defined that our perturbation is order Mach number squared smaller, this means that this term is just the derivative of the background pressure. Now normally when you do standard compressible hydrodynamics, you have to close your equations using an equation of state, because we have essentially more variables here than we have equations to solve for. So you have to close it with another set of equations. But here, instead of the equation of state, we're going to close our equations with a velocity divergence constraint. And we do this because this allows us to capture both the heating, the local compressibility effects due to heating in this S term, and it allows us to describe the background gradient here in this beta term here. So that's how we incorporate the assumptions that we've made in our approximation into our full set of equations. So I like to think that this equation kind of does the magic of the approximation. Okay, so how do we solve these equations? So we have our code moisture x. Yeah?
Sorry, but just go back one.
Yeah.
You said that instead of an equation of state, you express the velocity divergence. If you want to do this for like degenerate matter, where does that equation of state come in?
What do you mean degenerate matter?
Well, with a general equation, I hope this is a well-posed question, but with like a general equation of state like you would use for astrophysics or something. Does that...
So these are all the equations that we're solving for in order to evolve our system.
So I think the answer to Alan's question is that's in beta.
It's in beta? Okay.
Yeah, so all of the properties of like the reactions and stuff come in here.
Well, the thermodynamics, that gamma 1 there, is the generalization of this to a general equation of state.
Okay. So that gamma 1 is the gamma out of the equation of state, not just defined from like the sound speed or something like that. Okay, no, that's a good answer. That's
yeah, so for an ideal gas, that will be equal to the lowercase gamma.
Right.
Okay, so we're going to solve these equations using moisture x. So this is kind of an updated version of our previous code, moisture, hence why this one has got an EX on the end. So this code is a high-resolution, multi-dimensional, it's going to enable us to do high-resolution, multi-dimensional, long timescale simulations. And it's built on top of the MRX library. So this is an adaptive mesh refinement library. So it's going to do all of the clever stuff to do with generating grids and stuff like that for us, which is great because it means we just get to concentrate on the physics. We're going to use low Mach number methods in our code, as I've mentioned in previous slides. This code has been optimized for high-performance computing. So this code can run using MPI and OpenMP, or it can also run on GPUs. So I'll talk a bit about this at the end, but we're doing a lot of work at the moment to try and really optimize this code for GPUs. So we're going to use a large-ish reaction network, and this is implemented using our microphysics library. I say large-ish because it's more than 2, but it's a lot less than the hundreds of nuclei that some people model in one-dimensional codes. And it's open source, so all of our code is up on GitHub and free for anyone to download. Okay, so first application that I'm going to talk about of these low Mach number methods is massive stars. So a brief background for people who are maybe less familiar with massive stars is if you have a really large star, so I say really large, if you have a large star, which is maybe 10, 15, 18 solar masses, then when it gets to the end of its life, it develops lots of different layers of different compositions. So it has, on the outside it has hydrogen, and then as you go inwards you get heavier and heavier elements, all burning in these different layers. So we have lots of different nuclei, which kind of have different fractions as you go throughout the star. And then within the interior of the star, we have convection. So in each of these shells, we have convection happening. So this is the opposite of the sun. So in the sun, you have convection happening in the outer layers, whereas if you have a massive star, you have convection in the inner layers. So the thing that we're really interested in is we really want to model the state of this star in the few minutes leading up to a supernova. So this is important because if you want to do a really good supernova simulation, you have to have really accurate initial data. Like, you really need to know what the composition and the structure of the star looks like before you explode it. So this is challenging because the flows, these convective flows within this star, are very low Mach numbers. So as I've mentioned previously, traditional compressible codes have a hard time modeling this. So another thing that we're also interested in is looking at how rotation alters structure of this star. So it's thought that rotation will change the way that the different layers mix together. So if you have two different layers and they're kind of moving up against each other, you're going to get some interaction. And this is important because it's going to change the amount of fuel that's available in each of these layers. So it could change quite significantly the structure of the star in the lead up to supernova. So in order to really get an accurate simulation of this, you need several things, which I think I've mentioned before. We need high resolution, because we really want to be able to capture these turbulent mixing at these shell boundaries accurately. We need quite a large reaction network. So we need, as I showed on the previous slide, we have all these different shells with different nuclei burning. So we need a reaction network that doesn't just include a couple of species, it has to have multiple species all the way up to iron. We really need to do this in 3 dimensions. So lots of people have done models previously using one-dimensional codes, but we've got lots of multi-dimensional physics here. We've got convection, which is intrinsically 3-dimensional. We've got turbulence, which again, 3-dimensional turbulence can only be modeled using a 3-dimensional code. And finally, we need to do fairly long timescales. So realistically, this means we need to have several convective turnover timescales, so a few minutes of simulation time. So this is all very challenging to do using a standard compressible code, which is why we are trying to do this using Maestro. Okay, so the first few models that we've done using Maestro X, we've taken 1D initial data from a code called MESA, given to us by some people from MSU. And this is of a 15 solar mass star near to core collapse. So we take this one-dimensional data and we interpolate it, and we have to be very careful here to preserve hydrostatic equilibrium, otherwise all sorts of unstable things can happen. And we use this as initial data for our spherical state. And we're then going to evolve it using a 21 species network. So instead of using a largish network, 21 species is basically kind of like the largest one we can do, which kind of accurately models the physics, but doesn't completely kill our computer in terms of memory requirements. And that's implemented using our microphysics library. So this is what the model looks like. All these different lines are different species, and I see it kind of, the color's not so great on the screen. But you can see we have these 21 species. So here at the bottom, I've got the log of the radius of the star. And here I've got the mass fraction of the different species. So to the left here we have the core. So this looks quite large in this plot, but remember it's a log scale, so this is actually a really tiny part of the star. And then as we go through, you can basically see, the point of this plot I'm trying to show here is it's quite complicated. So we have all these different shells with different fractions. Some of them are very, very small on this plot. Again, log scale is very deceptive. But yeah, essentially, it's quite a complicated model. So the equations that I showed you before, they didn't include any rotation. So if we want to be able to model this, we need to include rotation in our models. And there's kind of several avenues that we're trying to explore in order to do this, kind of going from easiest to hardest. So the easiest way that we can try and include rotation in our models is we can just ignore the centrifugal force entirely. So if our star is rotating fairly slowly, as we believe it is, then we can just ignore centrifugal force and only model the Coriolis force. So this is pretty easy. We essentially just need to add one source term to our equations and it kind of seems to work. But if we want to model something that's maybe going a bit faster, then this is not really going to be that great. In order to do that, we might need to go on to the next kind of thing. So here, our next idea is to introduce a new pressure term which will capture the centrifugal force. And this new pressure is essentially kind of like, it captures the pressure due to the centrifugal force and will balance centrifugal potential. So just like the hedges at equilibrium, we have a background base pressure here. Here we're going to introduce a new pressure term, this P1, and that's defined by our centrifugal pressure, our effective centrifugal pressure. And that, if we add the gradients together, then we can define an effective potential for them.
Can I? So I guess I missed something. So you're modeling this rotating star under gravity, but why doesn't the centrifugal force just happen automatically? Why doesn't it just emerge from the dynamics?
So we model in the co-rotating frame.
You
You model in the co-rotating frame.
so your frame
there's
of
an
reference
explicit-
is rotating with the star.
Yeah. But the main issue is that we want the star to be spherical and the centrifugal force will
make it
deform
light.
it. Yeah.
Okay.
So her 4 steps here are basically ways to combat that.
So okay, so you can sort of look at it as a transformation of the coordinate system. Okay.
Right.
Okay.
Okay, so the next one is kind of a more explicit transformation of the coordinate system. So here, if we do want to have a star that's rotating fairly quickly, then it's the kind of when a spherical object rotates fast, it tends to bulge around the center, so it becomes oblate. And this means that the surfaces of constant gravity no longer line up with the surfaces of constant pressure. So one way that we can do this is that we can rewrite our base state in terms of these surfaces of constant gravity, so in terms of these equipotentials instead. So this basically means that we can pretend that the star is spherical, but in reality it's bulging because it's rotating quite quickly. So I've explored this and the equations look horrible, but it should be possible to put this in our code with a bit of effort.
And if Alice thinks they look horrible, then they really must be horrible.
So how does it compare to the horror of general relativity?
Oh, nothing compared to that.
So then that's a week's work for you.
But yes, and then the last step, which we kind of really don't want to have to do because it will mean completely rewriting our code, would be rewriting our base state as a 2-dimensional base state. So it's not only a function of the radius of the star, it's also a function of the longitude of the star. No, latitude. I always go the wrong way around. So this really will explicitly capture the oblateness of the star. But I haven't started looking at this because I'm scared. So we really don't want to have to do this, but If you did want to model something that's really fast rotating, so for example, if you want to look at neutron stars, which I'll be talking about in a bit, those rotate several hundred times per second. So really for those, lateness of the star does become important. So it might be if we do go on to look at those, and look at particularly the fast rotating ones, this might become a bit more of an important thing to do. But hopefully we can use some of the easier methods instead, but who knows. Anyway, so we've been doing some initial models, and basically for the last year or so, I've been trying to get the star to stably burn and not explode.
Isn't it
Because
supposed to explode?
not in our simulations.
Oh.
We're supposed to get up to the point just before it explodes. When it starts exploding, the low Mach number approximation is no longer valid. So we're trying really hard not to get it to explode. And when I say explode, it basically means the code seg faults.
Unstable.
So unfortunately, in our initial time sets, we basically found that the nuclear burning in the core is incredibly energetic. And this means that the time step, instead of being set by the hydrodynamic timescale, it's set by the nuclear burning timescale. And this is really annoying because the whole point of the low Mach number approximation is we're trying to take the hydrodynamic timescale and make that a lot longer by filtering out sound waves. But if even the nuclear burning timescale is shorter than that still, then that kind of means like, what is even the point of the low Mach number approximation anyway? So this has been incredibly annoying. And we think that this is happening because the equations are in nuclear statistical equilibrium in the core. So essentially you have some very energetic reactions happening one way, and they're almost exactly balanced by very energetic reactions happening in the other direction. So overall, nothing is really happening, but because our code is trying to capture these very energetic reactions happening both ways, the solver is finding it really difficult.
Is that just saying the equations are stiff in some
Yes,
sense?
yeah. The equations are really stiff. So it's using these really tiny time steps to try and capture them. So kind of the default way that we were solving these reactions is using strand splitting. So this is a common method used to model source terms in hydrodynamics codes. And essentially it means you kind of react through half a time step, then you do the non-reactive, the whole time step of like the hydro, and then you add on the other half of the reactions at the end. So if we look at this plot here, the strand splitting method is shown in blue. So what I'm showing here is for, at the bottom we've got time. On the left axis we've got this mass fraction of helium here. So kind of the thing we want is we want this nice smooth curve through the top. That's kind of closest to what we think the true solution is. But if we look at what the strand splitting method does, is it kind of swings wildly back and forth every half time step. So it's kind of going way off the true solution. Then we model the hydro, and then it's pulled all the way back to the true solution at the end of the time step. And each one of these blue points is like a call to the solver, and it's having to do lots and lots of work in these regions to try and pull it back to the true solution. So essentially, the strand solver is really struggling to model these really stiff reactions. There's another code that people in our group work on called Castro. So this is a fully compressible code. And that's kind of the code that is kind of the first one that we try out these new numerical methods in. And people in our group have been doing a lot of work on what's called spectral deferred corrections, or SDC. And this is a way of coupling reactions much more closely with the hydrodynamics. And it turns out that these can cope much better with these really stiff reactions. So these orange dots here are actually the calls to the SDC solver, and we can see that we get a much smoother thing here. So it's not pulled way off the true solution like the strand splitting method is, and it actually has to do far fewer calls to the solver. So it's not only more accurate, but it's a lot cheaper to do. So it means it can take up to 10 times larger time steps. So this is really good for us, because if we're being constrained by this really short nuclear timescale that the strand splitting solver requires, if you can use much larger timescale, then maybe instead we're going to be hydrodynamics limited, and that's where using the low Mach number approximation is going to help us. So we've just started implementing this in Maestro, so we kind of have like what we call a simplified STC in at the moment, and we're really hoping this could help us better model this really energetic nuclear burning. Before I go on, and also another thing that we're looking into doing, which I haven't put on the slide, but we're looking at ways that we can maybe kind of not explicitly model the burning in the core. Because we're not actually that interested in the core itself, we're kind of really interested in the region just outside it. So the fact that we have these really energetic reactions in the core happening are kind of annoying for us. And we don't really care about them explicitly. So we look.
Well, finish your thought.
Yeah. So we're looking at ways that we can just capture the heating from these reactions, but not actually model the reactions themselves.
In your definition of core, as you just described it, is that where you assume NSE, and that's what leads to the stiffness? Or?
I mean, I've kind of, basically core is, I don't really have an explicit definition of core. Here, I've drawn this line just after the iron 54 peak.
Right, but there's no irony things above that, right?
No.
Okay.
Yeah, basically we cut off the burning when it starts getting really hard for our code. There's no like rigorous thing yet because we haven't done any like full simulations, but essentially we're really interested in particular in the silicon layer.
Yeah.
So that's this layer here.
Yep.
So we really want to be able to capture all of the burning that's happening there without capturing any of the burning that's happening here.
Well, just for what it's worth, the reason I asked that question is that the iron group stuff is in nuclear statistical equilibrium. You have a balance of very, very high reaction rates. And the silicon group stuff is a quasi-equilibrium. I mean, I may be telling you stuff that you're annoying, but if you could just, I suspect a lot of the stiffness follows from that NSE, and that might be a good, you could turn off reactions in some species, and a lot of it would go away.
Yeah, I mean, that's also something that will be good to do. I mean, I know less about nuclear physics, so that's why I'm not really talking so much about it. But we have kind of mentioned that maybe there might be more clever ways of doing the burning, which kind of take into account this in NSE, so we can kind of turn stuff off more intelligently that way.
Yeah, bingo. That's the point I'm just fishing for. If that's what you're doing.
But yeah, that would also be another way that we can do it. Cool. Okay, so the second astrophysical application I'm going to talk about is type 1 X-ray bursts. So this is actually what I did my PhD thesis on. So type 1 X-ray bursts are basically explosions that happen on the surfaces of neutron stars. So you have a neutron star, which in our lovely artist's impression here we have here, and it's in orbit around a star that's kind of around the mass of our sun. But because the neutron star has a really strong gravitational field, it pulls matter from its companion. This matter forms an accretion disk around the neutron star, and eventually it spirals in around and makes its way to the surface. Now this accretion is an ongoing process, so the matter builds up in this liquid surface layer of hydrogen and helium, and eventually as it builds and builds, it kind of gets hotter and hotter and more dense, and eventually it explodes. So you get nuclear fusion is triggered, and this is a runaway reaction. So very quickly, a flame spreads across a substantial, if not the entire surface of the star. So how do we know this happens? Well, we see them. So we've been seeing these type 1 X-ray bursts since the 70s, I think. And what they are, so here we've got what's called a light curve. So this is a plot of the X-ray radiation that we measure from this particular source here. So here we start off with a kind of persistent X-ray radiation from the star. And then very quickly we have this very sharp burst. So over the period, over about a second, we have the radiation going like increasing by a factor of at least 10. So we have this very, I think it's much more than that But yeah, the radiation basically really strongly increases in its magnitude. And then over the course of a few tens of seconds afterwards, we then have this gradual cooling. So the great thing about these type 1 X-ray bursts is we have kind of, I think, over 100 known sources now, and they happen every few hours to days. So we've literally got thousands and thousands of these observations of these things, which for astrophysics is pretty good going. Certainly more than
So much
super
better
noise.
than those Novae. Yeah, we would be patient.
Now an interesting feature that I will draw you, so as I'll mention a bit in the next few slides, is there's lots of kind of interesting subtle features of these bursts. So one that I'll show you just because this plot's here now is for lots of these bursts, we see what are called burst oscillations during the burst. So this plot here is a power spectrum, and it's showing you that we've got some pretty coherent oscillations in this burst happening at around 364 Hertz. And for this particular source, we know that is around the same as the rotation rate of the star. So these oscillations, as I'll show you a bit more in the next couple of slides, they can occur anywhere in this burst. So they can occur during this rise period, this increase in radiation, and they can also occur during this cooling period. Now the physics behind this burst is we think that this rise period, this increase, is where the flame starts at one point on the star, so it starts on a hot spot, and this 1 second increase, this is the entire time it takes for the flame to spread across the surface of the star. And then there's decay here is basically where the star is then cooling down again after it's all been on fire. Okay, so we observe, as I have just mentioned a bit, we observe a wide range of phenomena. So we see, not only do we see burst oscillations, so these coherent oscillations during the burst itself, we also see what are called frequency drifts. So sometimes these oscillations can drift in frequency over the course of a burst. We see what's called softening of X-ray radiation. So it might be that initially the X-ray radiation starts at very energetic wavelengths, and then over the course of the burst it can become less energetic. We can see multiple peaks, so sometimes the radiation goes up, goes down a bit, and then goes up again. We can see what are called superbursts. So superbursts are essentially the same as X-ray bursts, but everything's magnified by a factor of 1,000. So they're 1,000 times more energetic. They tend to be, the timescales are kind of 1,000 times longer, and they happen about 1,000 times less regularly. So instead of every few hours to days, they might happen every few months or years. We also have what's called photospheric radius expansion. So this is where the burst is so energetic it throws out the upper atmosphere of the neutron star and causes it to expand significantly. So this is kind of annoying because it means coming up with a physical model is very challenging. So you've got to explain all these different physical phenomena using a single model. So it's pretty difficult. And it also suggests we have multiple, possibly competing physical processes happening. Because we've got, not only do we have nuclear burning, so the actual nuclear fusion itself, so we've got to worry about the composition of the ocean. We've also got to worry about turbulence, because it's hydrodynamics, so there's turbulence. We've got to worry about rotation, because these stars are rotating every few hundred times per second. I think all but one source, the rotation period of the source has been 300 to 600 Hertz. So they're really fast rotating neutron stars. We've got to worry about magnetic fields. So these neutron stars have what are called weak magnetic fields, and they are only around 10 to the 8 Gauss. So that's 10 to the 8 times the magnetic field of the sun. So most neutron stars are thought to have magnetic fields more like 10 to the 12 Gauss, but I still think 10 to the 8 Gauss sounds quite strong to me, so yeah, we should probably take those into account at some point. And they also have strong gravitational fields. So neutron stars, they're not quite black holes, but they do have very strong gravitational fields, and you're taking something that's around the mass of the sun and squeezing it into something the size of Manhattan. So general relativity does start to become important. And especially if you have something that's really fast, really quickly rotating, and very, very compact, that's where you can get some really interesting general relativistic effects happening. Okay, so here's some more plots just to show you some of the more features that we observe in these type 1 exobursts. So this is what's called a dynamic power spectrum. So it's showing you the frequency oscillations, frequency of the oscillations we observe over time. And this is of two bursts. They're kind of put together on a single plot. So in reality, there are a few hours between them. And we can see that we have the frequency of these oscillations is changing on the order of a few hertz over the course of the burst. So basically what we think here is that we think that the possibly the burst is throwing out the atmosphere of the star, causing it to change in radius, and just conservation of angular momentum means it slows down when the atmosphere is thrown out, and then as it cools again and contracts, it then starts rotating a bit faster again. But these are quite puzzling, and to show just how puzzling they are, here are a few light curves and dynamic power spectrum of several different sources. And we can see, if we look at the green curves, these light curves, no two of them look the same. Like, some of them are more kind of spiky, I like to call it, than others. So they have much sharper peaks. Whereas if you look at this one, we've got a much more rounded peak here. If we look at the dynamic power spectrums, we can see these burst oscillations. There's really very little consistency between bursts. So for this one, we have no change in the frequency of the burst oscillations. For this one, quite clearly, we get a quite nice rounded frequency drift. Same for this one. For this particular source, we can see we'd have pretty incoherent oscillations at the start, then they kind of turn off, then they go and kind of converge on a single frequency. But basically there is although we have many different sources and many observations, there's very little consistency between them. And even between consecutive bursts from the same source, they can look completely different, or at least there can be significant changes. So this just means coming up with a single model to explain every burst we've ever seen is really hard, and maybe not a good idea, but certainly it becomes very hard to try and identify which physical processes are kind of the most important to model. Okay, so yes, we see lots of differences. The physics itself is very extreme, so it's very unlike kind of terrestrial physics, which is a lot better understood. There's a wide range of scales for these things as well. So not only do we have to worry about the large-scale dynamics, so the dynamics on the scale of the entire ocean of the neutron star, but we also have to worry about very small-scale stuff. So we have to worry about the actual nuclear burning itself. So we're modeling stuff from the scale of kilometers all the way down to centimeters. And this is really challenging to do computationally. Like with the previous physical system we looked at, we have to worry about multi-dimensional processes. So we have to worry about turbulence, we have to worry about convection, we have to worry about Coriolis force. And the thing that links it to the previous system is the flame propagates at low Mach number. So if we use standard compressible codes, then the propagation speed of our flame is going to be much less than the sound speed of the fluid. And this is basically because the neutron star ocean is so incredibly dense that it really drives, and so high pressure, it really drives up the sound speed. So although it's traveling at, I think it's like 10 to the 5 kilometers per second, centimeters per second. Well, it's traveling very fast. It's still a lot less than the sound speed of the fluid just because the fluid is so extreme. So in order to try and make these simulations tractable, we have to use certain approximations. So previously, using the previous iteration of Astro, people at Stony Brook used the low Mach number approximation to model these type 1 X-ray bursts. Now what we're doing at the moment is there's a bit of a cheat here that we're not actually using the Mach approximation currently. But we're currently trying to better understand the flame structure itself. And to do that, we're using our fully compressible code. And so far, we've been doing simulations in what are called 2.5D. So we're modeling we're doing a two-dimensional model, but we're still capturing the velocity out of the plane. And to do that with our simulations up to a couple of months ago, we were having to artificially boost certain properties of the flame in order to get the flame moving fast enough that we can kind of make the simulations tractable. Though we've kind of been doing lots of work optimizing our codes, we don't actually have to do this artificial boosting anymore, which is pretty cool. So here is a video of one of these simulations. So this is of one of the artificially boosted flames. So at the top here we have the temperature of the flame. Then we have what's called A bar. So this is kind of showing you the kind of mass fraction, kind of like average mass fraction of the species. Then we have the nuclear energy generation rate, and finally the velocity out of the plane. So basically, the thing to take from this, so if we look at the energy generation rate, we can see that the burning is basically mostly happening at the base of the flame, which kind of makes sense because that's where the density, temperature, and pressure is highest. The cool thing that we've seen in particular is this kind of this gradient in the shape of the front of the flame. Let me go back to maybe if I pause it. So just wait if I want to get it. Okay. Oh no. Okay, maybe I can pause it. Technical issues. But yeah, so so the front of the flame is actually at this gradient, which is quite cool, and all the reactions we can see happen kind of on this underside of the flame. And then finally, if we look at the bottom one here, we can see the vortex forming. So the red here is the velocity. I'm going to say out of the plane, but I never get this the right way around because I can't do geometry in my head. But you can basically see that we have this very turbulent flame happening, and it's producing this vortex shape, kind of like a hurricane, which is quite cool. So these are the simulations we've done up to now, but we're currently working on doing simulations without any artificial boosting, and we're looking at exploring other physics as well. Okay, so last part of my talk, I just want to talk about some of the technical improvements we've done to the code recently, namely our port to GPUs. So supercomputers are increasingly moving to GPUs in order to increase the performance of codes whilst minimizing power consumption. So essentially this means that anyone who wants to run on any of the next generation exascale computers is going to need to port their code to GPU to use those machines. So we've almost finished porting Maestro X to GPUs, and I've basically shamelessly been copying the approach that's been taken to do this for our compressible code cache. And the thing that we really want to make sure that we do when we do this port is we want to maintain performance portability. So we still want our code to run on CPUs, and that's because it means we can run it on local machines for testing purposes, and also there are still quite a few good supercomputers out there that are CPU based. And it also means that when the next new technology comes along that replaces GPUs, it means we're still, because we're trying to maintain portability, it hopefully should mean that we're kind of geared up to adapt to that next architecture as well. So this is a key thing that we want to maintain when we're doing this port to GPUs. So I said that our codes are built on this MRX framework. So I'm going to talk about how this parallelism is done in MRX. So if we just look at an MPI-based system, then when we take our total domain, we split it into grids, and each grid is given to a different MPI process. So this grid will be given to one MPI process, and this grid will be given to another one. If we then add on OpenMP, then for each one of these MPI processes, we'll split them up into several tiles, and each one of these tiles will be given to an OpenMP thread. So every MPI process manages several threads. Each thread is given a tile. Cool. Now for MPI and GPU, so each MPI process is given its own GPU to manage, and each one of the MPI tiles is split up into many, many different threads. And each GPU, and the GPU manages all of these different threads. So it's essentially like this one, except these tiles become much smaller because GPUs can have thousands and thousands of threads rather than maybe like 8 or so. So that's how we do parallelism in MRX. So I've learned many things whilst doing this conversion, and kind of the key thing that I've learned is that profiling is really important. So when I first, earlier this year, I was basically trying to optimize the code, and I discovered that kind of ignoring these sections here, around 75% of the time was taken up in this one function here, which I've circled in red. So I thought, why don't I just concentrate on this one function and try and optimize that as much as I can? So I tried all sorts of methods, and I hit upon, so all of the GPU stuff up to now has been done by running that part of the code in Fortran. So previously, all of the kind of high-level stuff is done in C++, and kind of the low-level hydrodynamics is all done in Fortran. So I tried, there's kind of a new interface that has been developed by the MRX people to do this instead with C++. And just for fun, I thought, why don't I try that? And I managed to increase the performance of that code so it ran 20 times faster just by using this different interface. So basically, profiling when it comes to GPU development is just very, very important. And then, so I continue this for some other functions and basically managed to half the runtime of the code overall just by converting a handful of functions that were kind of the slowest functions in our code. So here is a scaling plot showing the performance. So here I'm doing a weak scaling for this one of our test problems, and this is showing the mean time per time step against the number of nodes. So the top, these are kind of some tests that I performed before I started doing any of this optimization. And then at the bottom, this is after I converted kind of those slowest functions. And overall, the runtime, the mean time per time step has halved just by doing this kind of, this change from Fortran to C++. So yeah, profiling is great. Okay, so just to finish up, so many astrophysical flows have what we call a low Mach number, and this makes them really challenging to model using standard compressible methods. So one way that we can do that and get around this is using the low Mach number approximation, which filters out sound waves and allows us to model these flows in a much less computationally expensive way. The way we do that is using Maestro X, which is our open source low Mach number solar hydro code. And this code has been optimized for HPC, so you can run it on all of the new fun supercomputers, including ones with GPUs. So I in particular have been modeling low Mach number flows in stellar convection and also X-ray bursts. And in the future, we hope to extend our solver to include effects such as MHGs. This will be important for the neutron stars. And we also want to include more higher order methods such as SDC to better model the burning. Thank you for listening.
We got some questions out of the way during the talk. Do we have more questions for Alex? Be shy.
So I may have a question. I didn't remember if you have talked about this. So in your code, do you, I want to know why you do the dev-u iteration before your calculation.
Why do you want to?
Not like the dev, this is the velocity, the dev-u iteration.
Div-u.
Yes, iteration.
So that's all about how we enforce a divergence constraint.
So, yeah, is it possible, so if I give you a very large velocity, makes the Mach number very large, and it will destroy your system?
If you try to model something with a very large velocity using these equations, then the approximation is no longer valid. So it might be that the code runs, but it's not giving you a physically reasonable solution.
I see.
The other aspect is when you set an initial velocity field, like your initial conditions, it also has to satisfy that divergence constraint. And so some of that cleaning is done before the simulation.
Yes.
Yeah, so that's what the diffuse iterations do at the start of the code. They're trying to really enforce this constraint. Yeah.
I have a question. So your background pressure, is it run for only one time for the whole calculation, or you run?
No, so the background pressure is a function of both radius and time, so it can evolve in time.
So your beta will also evolve as well. Beta 0 here. It
Yes.
is a function of radius as well.
Yes, like as a function of time.
Well, Alice hangs out in the ESS building, so you can always go and chat with her. And she's one of our local GPU experts as well. So if anybody has questions about HPC stuff, she is someone to talk to. Let's thank Alice again.